Okay, now we have the recording. So for today, the plan was talking about two things, which quite different, but again, I was trying to prioritize giving you some kind of idea and main motivations and explaining general things and how they connect to physical problems and also topics that will show up into an event that will be happening here in São Paulo next week. So I want to talk today, like finishing this more AQFT section, to mention Bisogniano-Wichmann theorem and talking about a little relative entropy and how does it connect to modular theory. For that, let me start first like disclaiming what is or like reminding you of what we are talking about and what is really Bisogniano about. So remember, it's a local net that's associated to every region. Okay, so I get just a message of unstable connection. I hope it's back to how it should be. So it goes from R1D minus 1, yeah, so it's Minkowski spacetime, and I get like for every region of Minkowski spacetime, I can find some algebra which has the information about the local observables, and they are all represented in the same Hilbert space. So as bounded operators in the same Hilbert space. Okay, so what's the properties that we had? We have like isotony. O prime implies the algebra for the smaller is contained in the algebra for the bigger one. We have Einstein's locality. So that's the, oh, sorry, O1, O2. I just put primes where I shouldn't. 1, 2, O prime. So if the regions are causally separated, they should commute. And here I want to stress the role that the Tomita Takesaki theorem plays, because in some sense I can recognize what is the sorry, so it's O is in O prime. That means that the algebra of O is contained in, so they commute with the algebra for O prime. So the role that Tomita Takesaki plays because of the J in this situation, right? So it's remember that if you have like a vacuum state that we call omega, and you conjugate the region O with this J, it gives me the commutant. Yeah, so okay, many ways of writing this relation. So just to say, okay, I will just change. So if O is contained in the, oh, that was correct. So one thing that I learned from this relation is that if I take the modular operator with one of these cyclic and separating vectors for this region O, I get the commutant of the algebra. So the Tomita, the modular conjugation has some kind of like natural way of relating regions or the commutant of an algebra with something else, which gives you information about Einstein's locality. Later, I will tell a little bit more of how this operator should be implemented. It's part of the Bisogniano-Wichmann property. And another thing is that, like, if you have the proper Poincare group, like for every G in the proper, I think I have to remember where I think it's to put the arrow below and the plus above. So for every element of the proper Poincare group, I was supposing to have some unitary G that when it acts in my algebra with this G or G star or G minus one, it just acts geometrically. So again, now some new information kicks in. Yeah, so that's the one parameter unitary group acts geometrically. And we just learned it from modular theory that in addition to these properties of the commutant, I also get some extra group. So this delta IT related to, well, the state or the standard subspace. Before I was denoting the standard subspace, here I'm denoting omega, just to say it's the standard subspace associated to the algebra O and the state omega. So this operator, which is an automorphism of my algebra, sorry, I missed the part in the other side, so it's delta minus IT omega is equal to A of O. And one can think, okay, now I have this extra one parameter group, which in some sense, as I told you, has to do with some dynamics in the sense that now the state omega, which was cyclic and separating, is a thermal equilibrium state for this one parameter group. Introduces some kind of new element. Yeah, so it's another unitary group. So what's the relation between the Poincare group and this group? Yeah, or what's how those things are connected? Yeah, so it's is it like something completely new? Is something known? So what is this one parameter group? So just to also mention some historical or like ideological design. So people know these things had to be strongly connected, could just not be kind of like, okay, it's a little bit lucky or like coincidence, but this modular group could not be something completely strange with no physical meaning, just because, as I mentioned, it has to do with thermal equilibrium states. So this group that one constructs purely mathematical, from a purely mathematical point of view, do have some physical interpretation as a thermal equilibrium, so it cannot be unphysical one parameter group. So what could that be? And that's precisely the answer that is that's answered in the theorem by Bisognano and Wichmann. So that's which I'm also not proving, but I hope you have appreciated I proved some properties and some stuff, but I also guess you note that even for proving these basic results, one has to be quite fast. So I try to give you like a kind of a feeling how the theory works, but these like very powerful main theorems, it will not be enough time for really covering it. So in some sense, I ask for forgiveness and understanding that I cannot really like I like to have like proof-based courses, but for many courses, one has to decide what to leave out. Otherwise, it is impossible to really make something understandable with the time frame. So Bisognano and Wichmann. Let's check that I wrote the names correctly. Yes, I did. So what does it say? That if so okay, I will write it and then I will tell what I'm talking about. So it's a modular operator, but related to, I'm writing here JW and delta W. So the modular data denote the modular data of the pair. And what is the pair? It's like I will take an algebra to this region W, and this region W, I think that's you notice that I'm changing the name, so I always call it the region O. So there should be a good reason for changing the name for W, and the reason is because I want this W to be a wedge. Yeah, so I'm thinking in Minkowski spacetime. Yeah, so the theorem was originally proved in Minkowski spacetime. Later, it was a little generalized for Friedman-Robertson-Walker type of metrics. So it's a paper by Sewell that showed that. So basically, Bisweno-Wichmann holds in a little bit more generality. It's not true for all spacetimes. Yeah, so that's the proof has some kind of restricted um, framework, but I would say it's good enough for intuition. So you have the pair, which is the algebra for a wedge, and uh, the state, the cyclic and separating state. Then what is W or what's JW? Well, this is theta times U of R to 3, 0 and delta IT. W is U of lambda W of T 0. So, okay, then you should ask, okay, what are those things? So U is precisely the the unitaries that you get from the Poincare group. That's why I start reminding you of the properties, or at least the language that we were using. So here, what I'm saying is like J and delta, they have geometric interpretation. So again, we construct the whole thing in a purely mathematical way, let's say. Yeah, so you start with a state, you get a region, the vacuum is or the state is cyclic and separating for this region. For now, I'm taking the region to be a wedge. So in 1+1 dimension, sorry, yes, a 1+1 dimension, I can think, for example, of the right wedge in here. So that's my W. Which is in particular like invariant for translations to the right, but also in particular also invariant to the boosts, as you probably all know. You also probably also discovered that like I think I have mentioned that drawing is not my strongest skill. So maybe with the help of the computer, it improves a little, but not much. So you have our wedge. And let's now try to make a small drawing of the hyperbola, which is always suffering to me. Yeah, so this is the me trying to draw the orbits of the boosts. Okay, so what the theorem tells us is that delta is the unitary representation of the boosts. Yeah, so lambda W is the boost in the wedge. Yeah, so that's part of my Poincare group. So this delta is definitely not something unphysical. It's precisely the unitary that represents the boosts that you get from this construction, which should be quite surprising, I hope. Or okay, so you can also think like, what else could that be? Yeah, that's if you look to the Poincare group and you have this modular group, so what else could it be? Okay, so maybe for lack of other good candidates, that is natural, but proving it's definitely not easy. And what is J? So J is related to theta, and what is theta? So here, just say that so it's boosts. Oops. And so what is theta? Theta is the CPT or PCT. I'm not sure that's the other operator. And this one is the reflection. Okay, so J has to do with this operator that reflects both x and like x0 and x1 coordinate. Theta is the PCT, so that's the conjugation with well, parity, charge, and time. And so uh, uh, these two operators, both J and delta, they have geometric interpretations. So J, I'm not really sure. So how do you feel? about J, but for me it's a little bit more intuitive to think that J should be this operator, just from geometric reasons. If you think what is the so if you start with the wedge as your like a region, like here, allow me to just put the R just to say it's the right wedge. From here, I can associate the algebra with the right wedge. And after getting the algebra with the right wedge, I can construct a standard subspace related to the algebra with the right wedge and the vacuum. And you can ask, what is the symplectic complement, which is, of course, what you obtain by using the J. And well, remember that all these things are kind of connected because of the commutant. Yeah. So remember that by calculating JH, yeah, so here for simplicity, maybe I just should call it H. So if I use my modular J, which is exactly the J is the JW for that standard subspace, and you apply that into H, it should be H prime. And as I mentioned to you, it should be like the H prime should be precisely related to the commutant of the algebra, prime acting into omega closure. And if you think that geometrically it has to do with the like this, the commutant of the algebra has to be with the causal complement of the region W, one can guess that should be the causal complement of omega in W, which is the algebra with the left wedge applied into omega. So this thing here, so if this is W, so here is the left wedge, and with the left wedge, we can construct the algebra with the left, and this is equal, right? Like that's at least a good assumption of the algebra with the right prime. Yeah, so it's at least contains it, but it's most of the time it's equal. So that's called Hag duality. So one can wonder, or can at least like think, having this in mind that like, okay, so the J is somehow related to this, like from the algebraic point of view of mapping the algebra from the right wedge with the algebra on the left wedge, and they are related by the causal complements. One can see that this J has to do with some reflection, but it's also antilinear. So you have an anti-unitary operator that at least geometrically just looks like conjugating reflecting the region, like the wedge, and say, okay, so if you think about symmetries and what does it mean to flip the left and the right, and you think about this like basically that these symmetries have to be represented by linear and antilinear operators. So what could be J? And it has to be either P or PT or PCT or some combination of those. So if I remember correctly, in history, there was some guessing originally what J was, but it was always involving these operators. Yes, it was either reflection or reflection, like parity and time reflection. So it could be P, PT, or all those guesses were around. But in the end, the one that was true was that J should be the PCT and some spatial reflection. Yeah, so that's in some sense quite surprising. So that's what happens in here, okay, I'm getting the short version of, say, of the theorem because I'm not stating all the assumptions, but it here, like the original proof by Bisoyan and Wichmann, is done for Minkowski spacetime, yeah, so flat spacetime. Well, Minkowski to be precise, yeah. So that's so it's definitely not for all geometries, at least not that I am aware of. There are more geometries for which it's true, yeah. So that's um, as I mentioned, this paper by Sewell, including some type of Friedrich Hubbard-Tolson Walker type of metrics. They prove that it's also some version of Bisoyan-Wichmann theorem show up. But for here, I would just stop saying this modular data, at least into some relevant physical situations for nice geometry, it is related to geometric operations, mostly about like simplicity and reflection and the boosts. Okay, so quite a powerful theorem. Nowadays, you are often going to say people talk about Bisoyan-Wichmann property. And what would be Bisoyan-Wichmann property would be kind of reversing the way of looking to the problem. So Bisoyano, Bisoyano, Wichmann property. Uh, Property, yeah. It will say like basically taking this geometric action as an axiom. Yeah, so instead of like proving that it's true, one suppose that you have a geometric action of your modular data. Yeah, so that's similar to what we do with Heschlieder. Yeah, so nowadays we mostly assume that the vacuum is cyclic and separating and see what you can get out of that instead of proving that in some particular model the vacuum is cyclic and separating. Bisoyan-Wichmann is the same. So instead of like proving that Bisoyan-Wichmann holds, okay, we know some proofs, and it's not that it's uninteresting, but to say oftentimes people will suppose that Bisoyan-Wichmann property holds and try to derive properties or understanding better the algebras using that the modular data have geometric meaning. Maybe an interesting disclaimer is that not all modular data have geometric interpretation. Yeah? So one can construct geometric or this kind of modular operators into an abstract way without coming from regions. Yeah. So here is another important fact. Right? Notice that the region has to be the wedge. One can ask like, okay, so for example, can I calculate and try to understand what is the modular data for the double cone? And the answer is no. So it's a no. So very hard problem. Very like experienced people have tried. It's a very hard problem to determine what should be the modular data, not for the wedge, but for the double cone. It would be, well, quite interesting to know. But as you know, like the modular flux should behave much harder in a very different also from geometry perspective in this region. Yeah, here it's just this hyperbola, and here what should it do? I don't know. So that's, I don't know, should be some kind of like hyperbola that gets back accumulated into here. So that should be my flux. I don't know. Anyway, very hard problem to understand what's the modular data for a cone or for other reasons. But the wedge has this kind of like nice way of behaving where the flux of the modular operator just behaves as this hyperbola. And that's kind of what guarantee, like this nice geometric situation is what guarantees that we can calculate and determine what is the modular data and that it has physical or geometric meaning. Okay. yeah, so that's the kind of the final comment that I would like uh, to make into this situation with the more into the algebraic quantum field theory. Uh, I was mentioning that like it's not always geometric. This shows up, for example, in the works by Morinelli. Yeah, so in there you can see like he has constructed some example of like a modular operator or modular data that do not have geometric interpretation. So not all modular operators for like when you construct it abstractly come from uh, like physical geometric situations. So you have some which are just properties of your algebra. But in this nice situation, when you look to the algebra that one gets from a wedge in Minkowski spacetime, you do have a geometric interpretation. And okay, so it's therefore it's useful to look to the physical situation when um, the modular data have physical interpretation. Moving a little bit to the other topic that I want to discuss today. So I want to talk about, so let's just take my notes here. So I want to discuss a little bit about relative entropy or entropy in general, and how does it connect with modular data. Yes, so here. So where is the calculation I prepared before? And here, what I want to talk about is more like, okay, so most of the time, I think I mentioned that before, people are like supposing the existence of a trace. And in some sense, I wanted to show that like how is this trace situation connected to some other type of modular data, namely what we called the relative modular operator. So sorry, I'm always like fighting with the computer. Like I prepared the calculations before so I don't get messed up in the presentation, and then the computer does something that's second. Yes, okay. Yeah, so um, so this part like has more to do with these ideas of like well, as mentioned, relative entropy. And here I want to discuss about like a little bit more general situation with modular theory, because when you look to the operator with, so maybe just call it like relative modular theory. So originally we have talked about like this operator S0 that goes from my von Neumann algebra with a cyclic vector omega, and I go to my Hilbert space, and basically what I do is like I get an operator acting to omega, and I get the star. So if you think about a way of trying to generalize this same type of operator, we can basically look to a situation where instead of having one vector, one have two. So one of your colleagues wrote to me some interesting questions about like when you look to Heschlida, how does it really, because it always gives you the impression that like regions, like different regions of space-time are kind of interconnected, which is very true. And that's basically why Heschlida works. Yeah, so the vacuum is very non-local in some sense. Yes, there's kind of information connecting different regions. Um, but we cannot talk, for example, about relative entropy or mutual information or whatever things of this type, because, well, the state is just one. Yeah, so it's just the vacuum. So if I want to talk about entropy, I want to compare two states. So what are these two states? So I need to look to two vectors, not only one. So I need to change my operator, and then I will just by simplicity write as 0. So I move the 0 to the upper part, and I will talk about the state phi2 and phi1. And I want to define this, look into these two vector states, which should be represented by vectors. I could even already maybe define in the vector, so omega 2, omega 1. It's easier to do that directly into the vectors instead of in the field, in the states. And I get an operator acting into omega 1, and I want to have the star, but I have the star in omega 2. If I make no assumptions about omega 1 and omega 2, this is definitely ill-defined. Yeah, so that's, as we saw, that very much depends on the fact that the states omega was cyclic and separating for having the Tomita operator. Yeah, so notice that if omega 1 and omega 2 are the same, and omega is cyclic and separating, this is just the usual Tomita operator I have defined long ago. So here, I would have issues to define what is this operator if I don't make any assumption about omega 1 and omega 2. But instead of making an assumption, I will change a little bit perspective and say, okay, I can look to a omega 1 bar, and I can define my operator not in this space only, but extend it a little. So it will be a in omega 1. So if it's not cyclic, then I will have orthogonal complement. Okay, and now this is almost the whole Hilbert space, but definitely dense. Yeah, because if there was a closure in here, that would be defined in the whole Hilbert space. But I'm missing the closure in here, which means that now it will be a densely defined operator. Okay, so how do I define my operator now in this domain, which is a dense domain in my Hilbert space? Well, I basically just get something of the sort an operator acting to omega 1 plus a vector into the orthogonal. And the part of the orthogonal, like the thing that depends on psi, I would just erase, meaning the orthogonal of that space would be in the kernel of this operator. Okay, now it's defined everywhere, so it's a densely defined operator. But so cyclicity, kind of, this takes care of the cyclicity. Yeah, it's a densely defined operator, but it's definitely not well defined because you can have more than one representative of the same vector if omega 1 is not separating. So how I deal with that, and that's a small trick which I will tell you how to solve, but I will also tell you how to, well, in which situation you don't need this trick. So what we do is we multiply by something called the support projection of the state or of the vector. And okay, I forgot this time. So what is, oops. So where SA omega 1 is the support projection of the vector omega 1 in the algebra A. And what is that? So this is the smallest projection leaving the vector omega 1 invariant. And so it's that is, sorry, the smallest projection in A leaving omega 1 invariant. Yeah, so for a von Neumann algebra, such a projection exists. It's called the support projection. And that makes my operator well-defined. Yeah, so that's this support projection being 1 means exactly that my vector is separating. Okay. For now, if you want to say, oh, I want to avoid understanding these support projections and whatever, you just say, okay, I just suppose omega 1 is separating. This thing here becomes an identity, and you don't have to deal with that. Yeah, but that's just to give you the most general situation. That's this one. Yeah, so you basically you guarantee that the vector is densely defined, meaning skipping cyclicity by defining it into the algebra or the algebra acting into the vector omega 1, but then you also consider the orthogonal complement. And in the image, for avoiding problems with the result of two different representatives giving different answers, you basically put a projection that tells that if the representative is the same, they will make it vanish. Yeah, so that's basically the role of this of the support projection. Okay, so again, if you suppose even omega 1 and omega 2 to be like omega 1 to be cyclic and omega 2 to be separating, then you don't have to worry about anything. Yeah, so that's then this orthogonal complement is 0 and the support projection is 1. Okay, so just for the ones that don't want to to look to the very technical details, you can just skip it. Okay, so as you can imagine, one thing that so why do we want this operator to be densely defined to start with? Is because I want to have the adjoint. Yeah, we have discussed that like the adjoint of operator is only well defined if the domain is dense. Yeah, because then you have a unique vector such that something happened thanks to Ries's representation theorem. And therefore, here we want to have a densely defined operator for being able to talk about the adjoint. And the interesting thing is that this operator is not only has an adjoint, as the adjoint is densely defined, and therefore this operator is closed. In fact, S0 omega 1, omega 2, omega 1 is closable, which means that in particular S0 star, omega 2, omega 1 is densely defined. Okay, well, as you all can imagine, that means that the closure of this operator, omega 1 or 2, omega 1, it has a polar decomposition where this thing here is a partial isometry. It's a partial, well, it's an anti-unitary operator. It's similar to what we have modular theory. Yeah, we have an operator that's well defined, but yes, so it's anti-unitary, and delta 1/2 to 1 is just the square root of S omega 2 omega 1 star times S omega 2 omega 1. Okay, nicely. So I have something very similar to modular theory, but it's not related to two operators. It's related to, not related to one state, it's related to two states. My question would be now, okay, so can I understand what is this modular operator into a situation that I know what entropy should be, or like relative entropy should be. So what is this operator into the situation when you have a trace, for example? And that's so just a second that I'm always fighting against the, oh, where is it? Just give me a second. Um, where is it? Save it. Just a second. For some reason, the notes I took were lost, it seems. But I have some saved in my drive, just so I don't mess it up with the calculation. Because if I start doing the calculations randomly without like defining things properly, it will be a big mess. Just give me a small second because I have it saved. Where is it? Second, I should also have some backups. Yep. Okay, let's have one backup. I hope that this one is. Yes. Well, where is it? Because I just want to do the calculation to this specific case. Oh, here. Yes. Okay. Sorry for the because I did this example in the notes and I just took in the computer because I worked from home and I was like having trouble to find the file. So that's for some reason the file was override for some other piece and that's anyway. So what I want to discuss is the situation. So that's maybe I can call it an example. So I want to discuss some kind of easy, let's say, situation when I have a tracial state. Like suppose A has a tracial state. Yeah, so maybe I need to make a small disclaimer. I'm not sure how you are all familiar with phenomenal algebras, but not all phenomenal algebras have a trace, not even unbounded one like the ones that you have in the bounded operators into a Hilbert space. Not every operator is trace class. Yeah, so the trace of an operator can give you infinity. So here I'm supposing I'm into an phenomenal algebra, which do have a bounded state, which is a trace. And by being a bounded state that's a trace, I just mean that it satisfies the cyclic property. Yeah, so you have this tau, which is the state. Yeah, so it's a positive functional, and you have tau of AB is the same thing of tau of BA. Yeah, so that satisfies the cyclic property. Okay. So in this situation, I want to look to two density matrices. Yeah, so my state phi into like a vector A, it will just be given by the inner product of some density matrix phi 1/2 in the vector omega, and then the A and then the H phi of 1/2. omega. Yeah, so that's basically how the state. So basically, I am using the GNS representation of my phenomenon algebra with the trace. Yeah, so in the phenomenon algebra, in the GNS representation, GNS representation of A with respect to tau. Yeah, so I'm taking this particular representation. Every state will be written in this way, right? So that would be the trace. Yeah, so that's basically, remember that the inner product in the GNS representation is just given by the state. So that's I'm calling tau of, and here, as you see, it's just H phi 1/2, A H phi 1/2, which because of the cyclic property is just trace of H phi, and then you pass the 1/2 to the other side for the cyclic property A. Okay, so why I made this small like explanation or the forward, just to tell you that basically I'm looking to a situation when I have density matrices. Yeah, so this H phi is the density matrix for the state phi. Yeah, so if I have a phenomenon algebra and a trace, I can look to the GNS construction. In the GNS construction, basically the inner product of any vector x, y, it comes from the completion of some specific vectors, yeah, so which are of the form A acting to omega, B acting into omega. It's nothing but the trace of A star B. Yeah, so that's you are probably familiar with this formula. For example, if you look to Hilbert-Schmidt operators, yeah, so that defines the Hilbert-Schmidt operators in terms of the like as a inner product space or a Hilbert space by defining exactly this inner product. So omega is like in the GNS representation is a vector that constructed using the trace. Yeah, so it's basically the vector that you get from identity in the algebra. But I don't want to go into too much details into the GNS construction. Just I hope you are all familiar and convinced that if you have like a normal state into a phenomenon algebra, it can be represented like with a phenomenon algebra with a trace. In the GNS representation, it can be represented as a density matrix. Okay, so let's see what happens if you have two states. Yeah, so I have now two states, phi and psi. So phi of A is exactly as I wrote. So in the GNS representation, it will be of this form. I have a second one, which is, of course, I want later to calculate the GNS represent the relative entropy. So this is just 8 psi 1/2 omega, and here I have A H psi 1/2 omega. And from here, you identify what is omega 1 and omega 2, the ones that define the vectors that I used in the relative modular operator, namely omega 1. So I can say, maybe I can just make some space and include the information. Oops. That's the advantage of these virtual blackboards. So what is this thing here is just omega 1, A omega 1, where omega 1 is just the vector H phi 1/2 omega. Okay, same thing for psi. So this is just omega 2, A omega 2, where omega 2 is equal to H phi H psi 1/2 omega. So you see that it's quite important to have a trace in the phenomenon algebra to begin with, because I needed to pass this H1/2 to the other side in order to be able to collect it in front to talk about the density matrix H, but also to talk about the vectors, which are given by the square root of the operator acting into the cyclic vector that we had from the um, from the trace. Okay, so I hope up to now nobody is seeing anything too strange or too complicated. So I would say that's basically the easiest situation we can have for states. Okay, so let's try to calculate what is the relative entropy between the states psi and phi, which is by definition the relative entropy, or sorry, the relative entropy, no, the relative Tomita operator between the vectors omega 2 and omega 1. So what does this thing here, this operator do into a vector of the form A acting into H phi 1/2 omega plus something of the orthogonal. Yeah, so remember how I defined my operator. My operator was defined as take something which is of the form an operator acting into your one vector plus something of the orthogonal, and that should be the result. Okay? So that's exactly what I'm doing. I'm getting something that is A applied to omega 1. Yeah, remember that omega 1 here is just this vector. So I'm being faithful to my definitions, and this other part should be in the orthogonal. And by definition, that should be, I know that my calligraphy sometimes make confusing what is the Tomita operator and what is the support projection, but that should be the support projection in the fundamental algebra A of the vector, yeah, or if you prefer, H phi omega, with the 1/2 missing, A star into H, and now it's H psi 1/2 omega. And here you recognize that this is omega 2. Okay, can I understand what is this operator? So can I express it in terms of something easier? And the answer is yes. So I can reconstruct it from omega 1 just with some kind of like a, let's say, simple operations. So let's see. So I want in some sense to, so see here, you have like a H phi 1/2 in omega, and I end up with a H psi 1/2 in omega. So how do I make like some kind of like a construction in such a way that it looks like, well, some natural operator, or like some, like, basically, how can I write that in terms of H phi and H psi? Yeah, so you get like a vector and what you really do. And allow me to write the result, and later I can tell you, explain the details. So that would be left multiplication with psi 1/2, right multiplication with H phi minus 1/2 into the vector X H phi 1/2 omega plus Y. So allow me to do the reverse calculation. So let me tell you, just I told you the names, but let me tell you what is this operator. So this operator A with H phi 1/2, it gets a vector, like something that is, well, let's say a vector X which lives into the phenomenon algebra, so it's something of that sort. So it's maybe write with A is better, and it gives you h phi 1/2, or like okay, it's with the minus times A. Yeah, sorry, the other way around. So it's A times h phi minus 1/2. Yeah, so it multiplies from the left an operator with phi. Yeah, so if you have an operator, multiply it from the right with phi. So what is the left multiplication with h psi? It multiplies from the left with h psi 1/2. Yeah, so just for notation. Okay, so let's write what in this S tau is just the Tomita operator for the trace. Yeah, so that's for the which is basically just a star. So let's see what I get in here. So if you multiply, so I'm just doing the reverse calculation just to show you that what I'm claiming is true. So that tells you like, yeah, so get your operator in here and multiply it from the left with h minus 1/2. Okay, then this thing here should just be h phi, sorry, x minus, so h phi 1/2. And then you multiply with h phi minus 1/2 in omega. So these two things cancel out. And then you multiply it from the left with h psi 1/2. And this is something acting into omega. And I'm just telling you, then take a star of everything. And therefore, the result should be x star h psi 1/2. Remember that my density matrix is positive, so in particular self-adjoint. Therefore, this h 1/2 don't get a star, omega. Yeah, so I just reversed the meaning of the calculation. Multiply left, multiply right, take the star. So if you see the result by the definition, sorry, I put an X in there, it's an A. So A, O, A star. So if you look now to what I just calculated, you see that apart from the fact that it is the support projection missing, which I will clarify in a second, I get the same result. Yeah, so that's A star acting into h psi 1/2 of omega. Okay, so how does the support projection start existing? And what you haven't questioned me, not sure is because you are shy or because it's kind of like hidden in this math calculation, is that h phi do not need to be invertible. So I never assumed that. So, okay, sometimes I assume. So when I say that, so if I say that my state is faithful, meaning this phi of A is never zero unless A is zero itself, then my state is faithful. Yes, then my state is faithful. But it could well be that, for example, phi 1 is in the kernel of A, and therefore it gives me zero. So this phi is faithful, yeah, meaning it doesn't vanish unless A is zero, is equivalent to say that h phi is invertible. Yeah, so meaning when you calculate this h phi in omega, it never gives you the zero vector. This is not always true. So it's not always true that phi is invertible. So I can write here h phi minus 1/2. Yeah, so that's you define it. So let me give you a definition. what should be h phi minus 1/2, and that should be the integral in the positive real line without zero. So I'm removing the zero of the spectral projections. So it's lambda dE lambda with respect to h phi, and here I have minus 1/2. So this operator is well defined. Okay, looks a strange operator. So what it really does? Well, basically it do the following. In the orthogonal of the kernel, so this is h phi restricted to the kernel of h phi orthogonal. So when you restrict to the orthogonal of the kernel, meaning the closure of the range, this is injective. Same thing for this guy. And more than that, it is invertible. So I can just get the inverse or the square root of the inverse of this one in the range. And what do you do in the orthogonal of the range, meaning the kernel? Then it's 0. Okay, so I'm basically saying in the orthogonal of the kernel, I don't care, that's 0. Yeah, so okay, but then when you apply h phi times h phi minus 1/2, you don't get the identity because h phi 1/2 has a kernel. And this, what we get in the end is the projection into the range of h phi, but the projection into the range of h phi is precisely the support projection. So what I wrote in here was a little bit wrong. So this is the support projection in my phenomenon algebra of h phi, or well, h phi, or which is the same thing as the support projection. Yeah, so of h phi in omega. Yes, just because it's okay, it's the operator, it's the support projection of the operator, but turns out to be the same thing as this one. Okay, so when I get the star, remember that it's very close to omega. When I get my star, I end up with some extra thing here. Again, if you suppose that the support projection is 1, you don't have to worry. But that's I'm just being very precise and a little bit more general. Since I can. Since it's a projection, it's also equals to its own star, h phi 1/2 omega. And in fact, then I am safe. Furthermore, these vectors, when applied to y, they do give you 0. Okay, so I'm not going to do the full calculation, but it's just simply a fact. Okay, so what I learned is that I can identify my Tomita operator, the relative Tomita operator. Oops, hence. The relative Tomita operator, omega 2, omega 1, is exactly equal to the Tomita operator for the trace, which is quite special. H psi 1/2, so you multiply from the left with h psi, and you multiply on the right with h phi, remembering that if h phi is not invertible, I have to take out the kernel. Now, just basically what we learn. Okay, so for the trace, remember that things in the trace commute, and that means that the modular operator is 1, which means that this thing here is already the anti-unitary involution. Yeah, just because for the trace, delta tau is equal to 1. So there is only a j. Therefore, this is already the polar decomposition of this operator. Yeah, so this is already your partial isometry, in fact, the anti-unitary involution. And this thing here is the square root of the modular operator. So the J as omega 2, omega 1 is the Tomita operator for the trace, and the delta H2, H1, 1/2, or well, even without the 1/2, I can just, it is just left multiplication by H phi, oh, no 1/2, right, with H phi minus 1. Yeah, so here I'm not taking the square. So if I take the square root, I have to take the square roots on the h's as well. Maybe a very careful student would just look and say, well, why is it true that the square root of the product is the product of the square roots? It doesn't sound quite right for operators, but it's true just because these two operators commute, right? So if you have like an operator A and you multiply on the left with H psi, and you multiply on the right with H phi, is the same thing if you do the other way around. Yeah, so multiplying one from the left and one from the right do commute. So those two operators commute, and therefore the square root of the product is the product of the square root. So I don't have to worry about non-commuting operators in this product. And that's quite an advantage. Yeah, so that's it do really helps one to calculate basically what we are going to calculate in the last few minutes. So how do I want to define my relative entropy? And here, since I'm using S to too many things, allow me to call this the entropy D. So D of the states phi and psi, maybe the bar, and this is Araki, what's called Araki's relative entropy. Relative entropy. And so remember that the formula above relies very heavily on the fact that I do have a trace in my phenomenon algebra, and then I can express my states as density matrices. So how to define relative entropy in the situation, for example, of a phenomenon algebra when we don't have a trace? Well, and then this is the proposition that Araki generalizes, and the suggestion is just like, oh yeah, so take the vector associated to the state phi. So I would, if I remember correctly, I call this one omega 1. And here we have another omega 1. So it's the expected value somehow in the GNS representation with respect to the state phi. And then you calculate the logarithm, so the natural logarithm of the Tomita operator, the modular operator of, sorry, the relative modular operator between these two states. Yeah, so that's delta psi phi. Just checking the name. Which is also delta omega 2 omega 1. Yeah, so just thinking the states represented. So why is it a good idea? So why should one, let's say, take this definition seriously? And is it like reasonable? So let's see what happens in the situation I just calculated. Yeah, so that's basically why I start with this kind of like strange calculation. Yeah, so like, okay, why do he want to calculate the Tomita operator in this specific situation? And the reason is because in this specific situation, I have a good intuition of what should be the relative entropy, and I want to check if this formula, which is much more general, because it just take the modular operator, which is defined in any von Neumann algebra, doesn't care which type or if you have a trace of or whatever, for two states. Yeah, so only with the fact that they are kind of compatible. And so what is that? So using the formula above, in the above situation, what is d of psi phi? And that's just minus omega 1 log of left multiplication with h, I think it's psi, so no 1/2. That's why I didn't put the 1/2. Yep. And then right multiplication with phi in omega 1. Well, but we just discussed that these two operators commute. And if two operators commute, the log is, well, basically, you can find like a common spectral measure for these two operators. So you can just decompose them as operators with the same spectral measure, which maybe you have heard us like, okay, two commute operators, you can find a common diagonal basis. That's not exactly the same thing, but exactly the same content. Okay, and then what is the log of the product? Since it's just will, so this thing here will just be the product of mu times lambda integrated with this common measure that makes these operators diagonal. And the log of the product is the sum of the logs. So that would be the log of L. Sorry, yes, so it's the log of L phi. I'm just thinking what's my preferred. Yeah, okay. So it's the log of phi psi plus, and I forgot the minus one here, the log of right multiplication with h phi minus 1. Yeah, just because the two operators commute. But they are also multiplication operators. Okay, one from the right, one from the left, but they are just multiplication operators. And I know what's the log of a multiplication operator, which is just the multiplication with the log of the density matrix plus the right multiplication with the log of h phi minus 1 omega 1, which is nothing but like minus h1. And then if I do the correct multiplication, so I multiply from the left with the log. So remember here we have 1. So we multiply from the left with the log of h psi. Just a second. So what is 8? So one extra step. So what is omega 1? So omega 1 by definition was just h phi 1/2. Yes, of omega. And here you have h phi 1/2 of omega. Yeah, okay, now it's correct. So now you multiply from the left with the logs. Yeah, so that should be multiplied from the left, it's log of h psi h phi 1/2, and then the omega is in here. And then I multiply from the right in this situation. So it would be minus, because here I'm just using the fact that the log of h phi to the power minus 1 is minus the log of phi of h. And then it would be h phi 1/2, and I multiply from the right with the log of h phi. Yeah, so the minus is this minus 1 in here. But of course, the log of h phi commutes with the h phi to the power 1/2. So this is omega 1, and then you have the log of h psi minus the log of h phi and h phi 1/2 into omega. And now I hope you recognize this formula. So when you calculate, so two ways of looking to that. So either you look uh, into the just saying that this is minus omega 1 log h psi minus log h phi again into omega 1. So basically it is the expected value into the state phi, let's say, because it's not really the state because it's extended to the whole Hilbert space, but it has to do with the state phi and the expected value of the difference of the logs. Or you can just look to that like from the trace point of view and say, oh, this thing here is just the trace or minus the trace of h phi 1/2 log h phi or h psi minus log h phi yes, so h phi 1/2, and then pass the 1/2 to the other side, and you can recognize this basically that this is the divergence, this Cougar-Leibler divergence. I always have a problem with spelling. Cougar-Leibler. Yeah, so Kullback-Leibler divergence, which is the usual definition of the relative entropy. Relative. So the upshot is that in the situation when I do have a trace and I do have density matrices, this proposition of Araki of defining the relative entropy for any two states into a phenomenon algebra this way guarantees that it reproduces the results in the more specific situation that's basically kind of intuitive. Yeah, so we can recover the results from the more, well, let's say the well-known situation from here. Okay, so I hope I have convinced you that Araki's relative entropy is the correct definition of entropy. One thing that like still up to being investigated. Okay, it's known, but I mean like just seeing the definition and seeing that it reproduces the previously known situation does not guarantee that it has all the nice properties that one would like to have, but it is true that this definition reproduces the nice results one have from entropy. Yeah. So, for example, it is like addictive. So, if you have like two separate systems and then you consider the relative entropy like for two like two systems put together, it's bigger than it's the sum of the other two. Yeah, so basically the properties I'm trying to find like here the other part of the document. Yeah, so today was the day of the technical problems. Um, No. Yeah, I'm having problem to find the comments about the properties. Yes, okay, now I find it. Yeah, so okay, so just some small comment about like, okay, so what is this? So just to tell what is that? So this Kubeck liberal divergence is just the usual situation when you have this when you have two probability distributions, you just define it as the integral of px and the logarithm of p of x divided by q of x. So this is the classical case with probabilities, which you kind of see that it's exactly equal to the definition I just gave you, and of p of x minus q of x dx. Which is equal to, well, it's, if you want to put the square roots, it's p of x 1/2 ln of p of x minus, oh, sorry, I lost the one I went here. Of q of x, yeah, ln of q of x, p of x 1/2 dx. Yeah, so in the commutative case, this is precisely the expected value with respect to the probability distribution p of the difference of the logs. So many ways of writing the same thing. So this is for the q of x. This is, I think that's I have 1, 2, 1, 2, 3. Too many round brackets. Okay, so just to tell you that like this situation with the trace, so the trace is played, like the role of the trace is played by the integral down there, or if you want like this, the expected value is in the state with respect to omega 1, so fixing the probability distribution is the same thing as fixing the expected value with the probability distribution p of the difference of the logs. So that's just the like one small comment that why those things are the same. And the properties that, like as I mentioned, like if we define the entropy, so Arak entropy, the way defined, it has all the good properties that one wants to have. So here, okay, now I find it. Some properties. So one, it's positive definite. So if you have d of psi phi is positive definite, meaning it's always positive and it's zero if and only if phi and psi is zero. And the reason has to do with modular theory. I can, okay, that's okay, I'm not going to full detail, but it's basically just because the modular operator do not have a kernel. Two, so if you have one von Neumann algebra, let's say, well, usually I use N and M for von Neumann algebras. It's just keeping A because of the beginning, but now I could put B in A. Okay, so you have, Okay, but B is the bounded operator, so allow me to go with N and M. B, a subalgebra. Of the phenomenon algebra N. Then the restriction sorry, and E N, a restriction um, from, so, okay, so what I mean by kind of restriction here, for the ones that are familiar, is a conditional expectation from M to N. Then, if you look to the state that you obtain by restricting the states psi and phi, yeah, so you are restricting the states for the subalgebra, yeah, so you have the state defined in the bigger algebra, and you restrict it to the smaller, so just kind of the restriction, even though I'm more interested in two conditional expectations. Then this is smaller than if you take the relative entropy related to the states in the bigger phenomenon algebra. And I would probably just like keep those two as the main uh, thing. Yeah, so it like basically if you restrict your state to a smaller phenomenon algebra, uh, your entropy is smaller. So bigger the algebra, bigger um, the entropy, and the relative entropy is always positive definite, which means it's some kind of like measure of the difference between phi and psi. Yeah, so that's basically it will only be zero if the two states are the same. A small comment that maybe you have noticed, like a small comment, is that the relative entropy is not symmetric. Yeah, so that's psi phi is usually different from S of phi psi. So one can see that, well, here for several reasons. First, you can first wonder if it's true that the Tomita operator from phi to psi is equal to psi to phi, and it's not always the case. But it can happen, yeah. So if you look into here, like just changing the logs, it's just change a sign, but also the state changes. Yeah, so it's there is an asymmetry here in the state, which is more visible when you look to to this formula here. Yeah, so it's with the trace. So here you clearly see that's like h phi gets some extra components. That's not only the difference between the two. Yeah, okay. So I think apart from the fact that it has like some nice statistical interpretation, that's what I would like to have tell you, like to have convinced you of the importance of modular theory. Yeah, so um, okay, so relative entropy is important because, as you probably know, like this phenomenon entropy is oftentimes not well defined because these operators are not trace class, or like well, one of these integrals or one of these logs can be divergent, even though the relative entropy is finite. Yeah, so oftentimes we are interested in comparing the entropy between the vacuum and some other state. And if you try to define the entropy of the vacuum alone, it can be ill-defined, so it gives you infinity, but you have very many states which have finite relative entropy. So that's one advantage of the vision of the relative entropy. Uh, another small comment, it has this kind of inference type of interpretation that's worth to be seen. So one of the ways of like interpreting classically this Kullback library divergence is basically if you have like kind of you believe your uh, uh, well your system to be in some given state and you make some kind of measurement, right? For example, if you have a dice which you believe to not be biased, and you start throwing the dice and get some results, how much do you believe your state is correct given what you have gotten? Yeah, and that's basically go with the exponential of the relative entropy. Yeah? So basically, if you start getting things which are consistent, your belief that you are in the correct state, so that's how I would phrase it, has to do with this relative entropy. Okay, quantum mechanically, I cannot give you a very physical intuition on the daily basis, but I think that's the classical one that helps seeing how those things work. Okay, so just like a small, like let's say, short version of what we have seen. So, like if you ask, okay, what have we learned in this Tomita Takesaki modular theory? So I started talking about okay, so what is the modular operator, but also why it is important. Yeah, so how local nets of phenomenon algebras give naturally rise under minimum assumptions to some vectors which have the property of being cyclic and separating. And being cyclic and
Pro-
separating allow. Yes?
Professor Ricardo, there is a question in the chat.
So let me just try to open. I'm always fighting with the chat that doesn't really open. Yes, in which other problems we could apply relative entropy approach apart into this vacuum set? Yeah, so good question. So usually it's also hard to calculate those things. Yeah, so you can imagine here I did a very like the as all good person giving a course, I do the very easy example, and the hard ones will be in the exercise sheet. That's okay. So no exercise sheet, but making this type of calculation in generality, like apart from this very easy kind of situation, is very hard. Yeah, because in particular in the situations we are talking, which is, for example, algebraic quantum field theory, when you have a local net, I've mentioned very en passant, like in passing, that the that the algebras should be of type 3. So there is in fact no trace around. So no, even not a semi-finite one. Yeah, so that's not only because I here I assume the state to be a tracial state, but even if you suppose it to be a tracial weight, meaning it can be infinity, uh, that's not the situation that you would have in reasonable local nets. Yeah, so they should be all factors of type 3, 1, which is the very problematic one precisely for not having a trace, or like that's one of way of framing it, or to say all the projections apart from the zero projection are equivalent of in the sense of Murray von Neumann. And therefore, when you are calculating these relative modular operators, you are always dealing with a very complicated situation, unless you are into a, let's say, more controlled kind of situation. Yeah? So if you're dealing with quantum information or spin glasses, then you may have a trace. Okay, so just giving you a reference, I always hate to give references that is basically myself. I have just like a paper published with collaborators, namely Gandalf Lechner, Max Hope, and Leonardo Sangaletti, about exactly this entropy approach. So that's in particular this calculation that I just showed you show up in there. So the paper is called like Integral Representations of F Divergences for General Phenomenon Algebras. Uh, and then you can see that these results are much more general than one anticipate. But why I'm talking about this There, I would do the calculation in a little bit more general situation when you can have a trace, which is just a tracial weight and not a tracial state. And that would be for the situation for what we call type 2 von Neumann algebras, and that, for example, spin glasses can be described in this type of algebra. Yeah, so basically what I'm trying to say is like if you are working with quantum information, you can be a type 1 von Neumann algebra, even if type 1n, which is just matrix algebra, and then these results hold in kind of generality. It's also true that you can do that in type 2 von Neumann algebras, which has, for example, applications in quantum statistical mechanics, spin glasses, and things of that sort. In true algebraic quantum field theory, of course, the results can also be applied. It's fully general, but things become much more complicated because no trace is around. But still, the Araki formula for the relative entropy, where have I? Okay, it's just some things ago. It still holds, yeah. So the formula is just general, but much more complicated to be calculated. And now, after this like 5-minute speech, let's precisely answer your question. But it's possible into some particular cases. If you look to the works, in particular, like Roberto Longo, I think with collaborators, I think Fabio Ciolli and Feng Shu and others, they often calculate the relative entropy between the vacuum and some coherent state. Yeah, so for coherent states, things that you can obtain from a unitary of the algebra. So basically, what I'm saying is that you can try to look what is the relative entropy between your vacuum and something that's obtained by a unitary in the von Neumann algebra and a unitary in the commutant of the von Neumann algebra applied to omega. So that would be my omega 1 and that would be my omega 2. So in this situation, the relative modular operator is much, much easier to be calculated, and one can obtain valuable information about the relative entropy of this situation, which means knowing entropy or relative entropy for coherent excitations of the vacuum in algebraic quantum field theory. So those are some of the applications. There are other that's like yes, so that can basically properties that one can think about entropy. I didn't went into full detail about modular theory, but like there are several characterizations of the modular operator, and some of them will give you precisely this idea that like entropy should be stationary for equilibrium states. Yeah, so that's remember that the modular operator is somehow related to equilibrium states, and therefore, in some sense, this entropy should be related. Well, it's clearly related to modular operator, in particular here, the relative one, so not only, but that's so the KMS condition is equivalent to some other conditions that look like the entropy should be stationary for equilibrium states. And I can go on almost forever with like this, like all types of things that you can imagine. There are people trying to make some kind of, I would say, some type of generalization, let's say, of this situation or modular theory for more geometric point of view. For example, Carl Hermann Neb and Vincenzo Morinelli, as I mentioned, they look to kind of defining standard subspaces and nets of standard subspaces, exactly trying to connect with physical applications from a Lie group and Lie algebra point of view, which would have like then bringing some more geometric perspective. Yeah, so as I mentioned, Roberto Longo and many other collaborations, Fabio Ciolli, Ruzzi, Vincenzo itself, try to look to this situation, conformal field theory. You have people that will, for example, be in this event here in São Paulo next week, like well, da Piaggi, and they have like a not too much into, I would say, not too much details into modular theory, but the algebraic approach for sure. They would do, well, for example, this bulk to boundary correspondence. So it's amazing how many things we can do with that. It's a very powerful tool. That I think that's getting more and more attention and have like a huge uh, field of applications that one can use. Yeah. So I myself, for example, I try to construct these local nets for, well, I'm not sure if I should record that because that's uh, basically speaking the bad part of this approach, which is the one I work with. So that's maybe I should not do bad advertisement, but it's true. So the main problem uh, into this, well, Tomita Takesaki, but the algebraic approach to quantum field theory is that it's very hard to construct interactive models, sorry, interactive, yeah, models. So describe interactive systems into the framework of algebraic quantum field theory. So in 4 dimensions, up to now, so what was the requirement? So it's 4 dimensions, interactive, and I think that's the only thing. There are no examples of these local nets. So the only thing that can be constructed up to now is free theory, which is weak part of that. From the strong, for example, this description of equilibrium states, so the KMS condition was the biggest positive point of view. But anyway, so going back to this construction, so what I try to do is exactly as a holy grail. Yeah, it's not. I'm not claiming that I'm doing having the result tomorrow, but like trying to understand better these nets in the idea of maybe one day being able to construct these local nets, or these Hag-Kastler nets for real physical models or reasonable physical models. Which by now exists in, for example, 1+1 dimension. I think also in 2+1 dimension, we have models which do have interaction, but not in the physical situation when you have 4. Yeah. So many things are still ongoing. And as I mentioned, I think now more people are looking to those to the algebraic approach, and I think it's quite positive, and many people are start learning Tomita Takesaki. So I think that's why I was invited to give this mini course, which I hope in a very short amount of time I have at least you a glance of what is modular theory about. I hope that I have convinced that it's very tricky from the mathematical point of view, but it's not just a mathematical thing. It's like physics demands this very careful treatment because, well, the physical situation lies precisely into the pathological case. Yeah, so it's everything just came out of that. Yeah, so we start with back to. So I hope I have answered Jenny question, even a little bit too long. But it connects very well what I was going through in this kind of review. So we motivated the necessity of these cyclic and separating vectors from Heschlida, which was derived from physical reasonable assumptions. And from that, we could make this Tomita Takesaki, which turned out to be almost out of lucky, uh, connected to equilibrium states or thermal equilibrium states, as proved by Haag, Hugenholtz, and Winiken. There is a famous, so if you go to so Haag has a book, which is in the bibliography I suggested for this course, which is called Local Quantum Physics. And in there is a citation, or like a sentence that I often cite into seminars and things, which goes a little bit like this. Like I don't know it precisely, like word by word, but it goes something like the Tomita Takesaki theorem is an example of pre-established harmony between physics and mathematics. And that's very true. So because in particular, the results and the KMS condition, the modular operator, and the equilibrium states, they satisfy the same property, and nobody expected before finding it. Yeah, so that's it was just kind of out of lucky that the two groups working from the mathematical and from the physical point of view discovered the same condition from very different reasons, one mathematical and one physical, and they turned out to be the same. Yeah, so that's quite a lucky situation. But anyway, then we construct this modular theory and we start finding very interesting applications. So the modular operator is related precisely to, well, in some sense, it measures the non-commutativity of your algebra with respect to the state. Yeah, so for example, for a trace in which inside the trace two operators commute because of the cyclic property, the modular operator is just identity. Which sections in this book we should read after the mini course finishes? Yeah, so I can just give a look into the book later, and I can send you some of the most interesting sections that you can easily try to give a look after this mini course. Yeah, I just would need to have a little bit more time, but with pleasure I can send you some references. Yeah, and so just to conclude, so from this modular operator, we end up with some very interesting structure for the phenomenon algebra, meaning out of a state which is, or a vector which is cyclic and separating, I could construct some one parameter group, namely the modular group, for which my state satisfy equilibrium condition, and I get an antilinear anti-unitary involution, which maps the algebra into the commutant, which is very well connected with Einstein's causality. Into some specific situations like Minkowski spacetime and the wedge, I could even prove, like me, I mean, Bizoyan and Wichmann, yeah, so it's not my results, but what I just like making a short version of what we have covered. So one can prove that in this specific situation, the modular group is nothing but the boosts. Yeah, so that's representation as the unitary representation of the boosts in your phenomenon algebra, and J is related to the CPT and some reflection. So both very geometrical. Furthermore, we could basically recover the usual definitions of relative entropy from the modular operator. More than that, usually the modular operator, in the case of the trace, it is the dense matrix. So somehow it is the natural replacement of the dense matrix when the dense matrix is not there. So one should definitely pay a lot of attention to modular theory, at least with my biased point of view. And so with this small final speech, I hope you all have enjoyed. I I'm sorry that sometimes I was a little bit like sketch to choose too confused and maybe hard to present the ideas. It's always complicated to try to make things look natural when you have too little time and you cannot really go into the detail. But I hope I have delivered and I have convinced you that it's a nice theory to look to, and we should all learn more modular theory. And yeah, so I hope that we meet into the near future, and that's it. So thank you very much for everybody attending. If you have any questions, we have like, I would say 2 more minutes, and maybe for the first day I can give Bruno the stage 2 minutes before his lecture starts. Yeah. Okay. Well, if it's not the case, I will start like passing like the word to Bruno. So let's stop recording. Yes.